Welcome to Evolution in Controls. I'm your host, Tim Wilson. Thank you for joining us. This is a special episode of Evolution in Controls. We're on site in Franklin, Wisconsin. We're here at the new value-add facilities for Yaskawa. We're here to talk about advanced drive technology and the Matrix family series of drives and a drive in that series. We're joined today to walk us through this technology is Jordan Engel. Jordan, thank you for joining me today.
Well, thanks for the introduction, Tim, and welcome to our facility.
Thank you. Now, you are product manager for this family, correct?
Yes, I'm the product manager for the U1000 Matrix family of drives.
All right. Tell us a little about yourself. How long have you been with Yaskawa? How long have you been in the industry? And then a little bit, what do you do as a product manager? What does it mean?
I've been at Yaskawa for about 8 years, but I've been in the industry for over 20.
All right. So this is not your first rodeo.
No, although most of my time has been spent in field sales. I was what they call a sales engineer.
Lowly sales engineer, is that what you're saying? And you got promoted up to a product manager?
Well, I was invited to move to Wisconsin and join the product management team here at the factory, yes.
Nice, nice. Well, thank you for taking time out today. You heard me in the introduction, advanced drive technology, the U1000 Matrix family. Tell me, and this is the U1000 here that we see. Tell me a little about it.
Yes, absolutely. To my right is a sample here of the U1000 Matrix. And when we talk about advanced drive technologies, this product stands apart from every other drive that's on the market today.
Okay, why?
Well, almost every other drive, to accomplish the output to the motor, we take AC power coming in from your supply, your line.
The line voltage.
Absolutely. We convert it to DC.
Yeah.
And then
back to AC.
We invert it back to AC. So that's why when someone refers to a drive as an inverter, they're specifically, perhaps unknowingly, referring to the DC to AC portion of the operation.
So are you saying that the U1000 doesn't do that?
No, it doesn't. It converts directly AC to AC by switching off the incoming line.
Interesting. So no DC component in there.
Nope.
So there's got to be a reason. There's got to be benefits. What are the benefits?
Well, to talk about the Matrix any further, perhaps we should revisit a standard, what we call 6-pulse variable frequency drive.
All right. Is that what's on the screen?
Absolutely. That's what's here on the screen. And Yaskawa, we have many models that we sell that are of this design, a 6-pulse drive. You have your incoming line voltage on the left.
It's a full-wave bridge then.
Yeah, you have a 6-diode, hence 6-pulse drive, rectifier, the converter section, where we convert that incoming AC voltage to DC.
And you've got an RC filter network there, resistor and capacitor.
Yeah, we have we have our DC bus capacitors, which are used to filter the output from the rectifier.
Then is that a regen IGBT and resistor?
Yeah, just to the right of the bus capacitor, you see the 7th IGBT. We call that the brake chopper, and then at the top of the screen would be the resistor where the heat would be dissipated.
And then that's the 6 devices, devices.
The output section, the inverter section of the drive, you have 6 IGBTs, 2 for each phase.
All right, so this is that's a traditional AC to DC to AC, back to AC drive.
This is your standard 6-pulse drive, and it works very well. It's a efficient design. It's a tried and true design.
So you cut out the AC to DC phase.
Right.
Does it give you benefits?
Yes, absolutely. So there's 2 primary benefits to the U1000 Matrix. One, it's a low harmonic drive.
Reduced harmonics.
Reduced harmonics. So if you have a standard drive like we see here on the screen, that drive will produce upwards of 88% THDI, that's total harmonic distorted current. The U1000 produces less than 5%.
Okay.
So all right. Big improvement.
And I'm guessing that part of that is because you've gotten rid of the AC to DC stage, right?
Absolutely. The DC bus capacitors, which are required to filter our output from the rectifier. As a consequence, they draw nonlinear current, which leads to the formation of harmonics.
Reactive energy.
Correct.
So that's one of the benefits. Is there another benefit?
Well, yes, and we'll talk about the other benefit later on in this discussion, but the U1000 is also a drive capable of full regeneration.
So this is the circuit then for the U1000?
Correct. So we just took a look at the 6-pulse standard drive schematic, and here on the right-hand side of our screen is the schematic of the U1000.
A lot more LGBTs.
Looks a lot different, doesn't it?
Mm-hmm.
Yeah, well, instead of AC to DC and DC to AC, you have 9 pairs of IGBTs, so that's 18 transistors in total, which connect your incoming line voltage to the motor terminals.
Okay. All right.
Now this drive operates on the principle that your 3 incoming phases of voltage are all out of phase with one another. So if you look on the screen in the lower left-hand side, you see your 3 incoming waveforms. Well, they're not all in phase. They're separated. They're
120 degrees out.
Absolutely.
Right.
So you take a look at a given point in time, your voltage difference between phase 1 and phase 2, and phase 2 and phase 3, and if you add those differences together, you get your full line voltage at any given point in time.
So you're just controlling what different pair or sets of IGBTs, whether they come on or not, right?
Absolutely. This matrix of IGBTs, which can connect any line to voltage to any motor terminal at any given time, allows us to create a 2-step waveform to the motor. Okay. The first step is phase 1 to phase 2.
Yeah.
The second one is phase 2 to phase 3.
And so it gives you a three level output pulse.
Absolutely.
Of the frequency that you want, though, right?
Yes. Yeah. By using pulse width modulation.
By deciding which phase you're going to connect.
Right.
Okay.
So on our screen in the lower right-hand side, is an example output from the U1000 matrix.
So traditional PWM voltage output.
And on the lower left-hand side is an example of the output of a standard 6-pulse drive. And we accomplish the same output, but we do it in a different way.
There's a lot less switching going on.
Well, there's actually more switching on the output side of the drive, but because we don't go from AC to DC, you don't have the switching of the diodes of the front end of a standard drive.
So I have less harmonics. Why do I care? What benefit does it bring me?
Harmonic currents are a form of reactive energy. And whether it's a drive, and drives aren't the only nonlinear load out there. We have LED power supplies, you have EV chargers, all kinds of examples of modern equipment that draw nonlinear current, which leads to the formation of harmonics. Those are additional reactive currents between your device and upstream, your power distribution network.
But if I'm not paying for power factor, it's not costing me anything in money.
Well, that depends on your relationship and specific connection to the utility. But even if you're not paying for that additional reactive energy, it's increasing heating in your upstream components.
Okay, so more harmonics gives me more I²R losses, is what you're saying.
Absolutely. And those I²R losses can contribute to voltage drops, which translate into voltage distortion.
Make the voltage dirty.
And that's what all the other devices connected to your network see as well.
Okay. Well, you said there was a couple of benefits. We talked about one.
Yep.
That's harmonics, heating, voltage distortion. What's the other one?
Well, the other one is the ability to continuously regenerate. You pointed out when we talked about the standard 6-pulse drive design that there was a 7th IGBT and a braking resistor.
Right.
Well, in that design, you can accommodate some level of braking or regeneration from the motor, but it's usually not continuously rated. And even if it was, you would be burning all of that heat off.
All you're doing is just dissipating it through heat.
Wasting energy.
Yeah.
The U1000 matrix, if you look on our screen, we have 9 pairs of IGBTs, and when you look closely, you see that they're complementary to one another.
That's what the other pairs are. They're
Right.
in the opposite polarity.
One side is a motoring IGBT. The other side of the pair is used for regeneration.
Okay. Now, there's going to be some harmonics that we're putting back onto the line, but because it's so reduced, it doesn't have an impact?
It has a minimal impact. If you look in the upper right-hand side of the screen, we see an input current waveform. The real bumpy one is the waveform to a standard VFD.
Right.
It's heavily distorted. The waveform below the blue arrow, looks almost entirely sinusoidal. That's what you can expect the input current waveform to a U1000 matrix to look like.
Okay. All right. Well, how long has this drive family been out? Or this drive, U1000?
This is actually the second generation.
Okay.
So
it's been out a while.
It has. The first generation was a limited release. We sold it to some specific customers.
Certain industries?
Right. And
industries that needed the continuous regen, like overhung loads or
escalators, you know, that type of market. And based on the initial success, the second generation was tailored to be a general purpose, high performance product for all customers to use. So if you have a customer where harmonics are a concern, using this drive will help them reduce their harmonic footprint. If you have a customer with continuous or a high frequency of regeneration, the U1000 can ultimately save you money there as well.
So is this drive in the prime of its life cycle? Is it time for an upgrade? What does the future look like?
This drive, the U1000, is in the prime of its life cycle. There will ultimately be a next generation low harmonic drive from Yaskawa, and we won't be going into details about that today.
Hey, wait a minute. You're not gonna slip us some advanced information on it?
No. The U1000 in its current form is well equipped to address the applications we see today.
Okay. So, you know, we're coming to the end of our time, but in the future, what does the future look like for this drive? It's in the prime of its life.
In general, well, this drive or any other, you look at efficiency, size, and the ability to connect with external equipment. Connectivity is a big deal these days.
IoT connectivity.
Yeah. The Internet of Things, exactly. So you take those three factors and you can pretty much look to where any next generation product.
Do you see the semiconductors changing so that the physical size of the drive changes?
Semiconductors continuously change, and better semiconductors have fewer losses.
Smaller drives.
Translates into a more compact product.
Well, maybe we'll come back in a couple of years and see what changes that, since you're not going to slip us any new information.
Well, we'd love to have you again, Tim.
All right. Jordan, thanks very much. Appreciate your time. To learn more about Yaskawa and the Matrix family series of drive from the U1000, visit yaskawa.com. To learn more about Evolution Motion and our products and systems and solutions, visit evolutionmotion.com. Don't forget to subscribe to Evolution in Controls on whatever platform you use for podcasts or on YouTube for a video version so you can be updated when we release new episodes. I'm Tim Wilson. Thank you again for joining us. And remember, keep moving.